Hello, this is Jules Milovich, and I'm going to be talking about geoengineering and Russ George's ocean fertilization. In 2012, entrepreneur Russ George dumped iron 2 sulfate into the ocean off the west coast of Canada. He had two main goals in mind. He wanted to increase the salmon population and to sequester carbon dioxide. His experiment was supported by the local Haida people, who paid him $2.5 million to dump the iron into the ocean. The Haida people had been economically impacted by a decrease in their local salmon population. It's thought that this decrease in the salmon population was due to fishing and to global warming. Russ George hoped the iron dust would stimulate an algae bloom, and that algae bloom in turn would encourage the salmon to feast on the algae, and the salmon could also feast on other animals that ate the algae. The increased salmon population would bring prosperity to the Haida people's local fishery. The algae bloom would also absorb carbon dioxide from the atmosphere via photosynthesis, and the algae not eaten would eventually die off and fall to the sea floor, hypothetically sequestering the carbon dioxide on the sea floor. The Haida people would also be able to sell carbon credits to businesses who would get permission to produce more carbon dioxide. What Russ George did is an example of geoengineering. Geoengineering is any deliberate, large-scale intervention put into the climate by humans to counteract climate change, also known as global warming. Russ George was looking into a specific type of geoengineering called carbon sequestering. Carbon sequestering aims to take excess carbon dioxide from the atmosphere and trap it down in the ocean floor or any other place where it can stay for millions of years. Carbon dioxide is a naturally occurring compound. It's a trace gas in the atmosphere. Carbon dioxide from the atmosphere cycles through the earth. Carbon dioxide can come from beneath the earth from volcanoes and geysers. It can be formed by the weathering of rocks over time, and it naturally occurs in bodies of water. Plants consume it. We breathe out carbon dioxide into the air when we respirate. Carbon dioxide is essential to life, as life on Earth is carbon-based. However, you could always have too much of a good thing, and that's where global warming comes in. Global warming occurs when excess gases, such as carbon dioxide, absorb sunlight in the Earth's atmosphere. The heat, energy, or radiation from the sun is trapped in the Earth's atmosphere with these gases, and that in turn makes the world hotter and is called the greenhouse effect. Too much carbon dioxide is causing global warming through the greenhouse effect. And it's generally accepted that these excess carbon dioxide emissions come from human pollution. Human actions such as the burning of fossil fuels, deforestation, put more carbon dioxide out into the atmosphere. Carbon dioxide levels in the atmosphere have greatly increased since 1800, around the time that the Industrial Revolution began. You can see in the red in these graphs where there's a huge spike due to increased human pollution. Global warming impacts the oceans as well. About 71% of the world is water, and the oceans hold about 96.5% of the water. The excess heat and gases from global warming get absorbed in the ocean, and the oceans have been absorbing about 90% of the heat from greenhouse gases and about 25% of the excess carbon dioxide gas itself. The reason that the oceans can absorb all this gas and heat is because oceans are huge and have a high specific heat capacity. This means it takes a lot of energy or heat to raise the temperature of water. Compared to other substances, water has a uniquely high specific heat capacity, about 4,182 joules per kilogram Celsius. It takes 1 calorie of heat energy to raise the temperature of 1 gram of water by 1 degree Celsius. Water's unique specific heat capacity is due to its molecular atomic makeup. Water is composed of 2 hydrogen atoms and 1 oxygen atom. The hydrogens and oxygens have different electronegativity values. Electronegativity is a measure of the ability of an atom to attract electrons when in a compound. Oxygen has an electronegativity value of 3.44. Hydrogen has an electronegativity value of 2.20. The difference in their values makes water a polar molecule. Polar molecules essentially have unbalanced charges, with a side of the molecule being slightly more negative and another side being slightly more positive. If you look at the fluid structure of water, you can see that oxygen has 2 lone pairs, The lone pairs of electrons on the oxygen repel each other because they are both negative, opposite charges attract, and similar charges repel. The two hydrogens are positive, and they also repel each other. So the two hydrogens try to spread apart, and the lone pairs on the oxygen spread apart. This gives the water molecule a bent shape. So one side of a water molecule has the partially positive charge by the hydrogens, and the other side is a partially negative charge by the oxygen. When you have a bunch of water molecules, they bond together through hydrogen bonding, which is a dipole-dipole attraction. In this picture, you can see that deltas are representing the dipoles, which are the partial charges in the polar molecule. Water molecules are constantly forming and breaking these bonds together. In this picture, you can see one molecule being attracted to another molecule of water. And since these bonds are constantly forming and breaking, water is able to flow past itself but also bond to itself. These bonds are also why liquid water has a high specific heat capacity. Any energy put toward heating water is split between breaking the bonds of the water and heating the water. Because of this, it takes more energy to heat water than it does other substances. And so, oceans are absorbing most of the heat of global warming. And this leads to rising ocean temperatures over time. Increasing ocean temperatures affect marine species and ecosystems. Rising temperatures affect the health of coral species, which are breeding grounds for marine fishes and mammals. The more coral killed, the less marine animals are able to breed. Rising ocean temperatures also affect any benefit humans may derive from the ocean. There'll be less food to harvest, there'll be more diseases among the food, there'll be more extreme weather events. The ocean, of course, is also absorbing the carbon dioxide, not just the heat. This diagram touches on an important effect that occurs because of this absorption: ocean acidification. Carbon emissions lead to ocean acidification. Acids are substances that donate protons. In a more general sense, they donate hydrogen cations, H+. A cation is a positive ion formed by the loss of an electron. An anion is a negative ion formed by the gain of an electron. Acids also lower the pH. pH is a measure of the concentration of these hydrogen ions. The more hydrogen ions, the more acidic a substance is, and the lower the pH. Carbon dioxide in the water and in the air is at an equilibrium. When carbon dioxide reacts with water, it yields carbonic acid. Carbonic acid then dissociates into bicarbonate and hydrogen cations. The bicarbonate ion further dissociates in the water to yield carbonate anions and more hydrogen cations. These dissociation reactions are producing this H+ ion, and having more H+ in the water lowers the pH and makes the water more acidic. To prevent drastic changes in pH, the ocean has a natural buffer system. Buffer systems use weak acids or bases to stem off large changes in H+ concentrations. Bases are the counterparts to acids. They raise pH. In the ocean, carbonate ions are the base used in the buffer to keep H+ concentrations in check. One source of these carbonate ions is calcium carbonate, which comes from discarded seashells and also from limestone rocks weathered over time. You can see in this diagram how everything is at an equilibrium, and adding more carbon dioxide affects the left side of the equation and shifts it towards the right. If you can add more carbonate from dissolved seashells or limestone rocks, you can see then it will shift it back towards the middle and the left. This follows Lestat's principle about equilibrium responding to stresses. That's what a buffering system does. It responds to these stresses. However, the more buffering the system has to do, because of more and more carbon dioxide entering the ocean and producing carbonic acid, the more carbonate will get used up in this process. Over time, the capacity of the buffering system is reduced and the ocean becomes acidic. Ocean acidification. One of the environmental impacts of ocean acidification is that more of the available carbonate in the sea is used up in the buffer system and leaves less for organisms to use in their shells. Species like oysters, lobsters, coral, anything that uses calcium carbonate to make shells and skeletons will have less of that available. These shelled organisms will be affected, and they will make less of each other. Some shells and skeletons can also dissolve if the ocean water becomes acidic enough. Acidification affects this population of shellfish and impacts consumers. Now, I'm focusing on just the ocean effects of global warming, and they are enough to make me say, we need to stop global warming. We need to reduce our carbon dioxide emission. Geoengineers, however, want to focus on counteracting the effects of the emission. Russ George and others work on carbon dioxide removal, which doesn't do anything to stop the source of the carbon emissions, it only counteracts those that are emitted. I mentioned before that carbon dioxide is naturally occurring. Here's an infographic that shows how carbon cycles through the planet. It's very complicated, and human activities have all become a much larger part of the cycle in recent centuries because of industrial activities. The ocean is a huge part of the carbon cycle. When we look at how carbon and carbon dioxide cycles through the ocean, we are looking at two pumps, the physical pump and the biological pump. The physical pump has to do with currents. In downwelling currents, cold and dense water takes dissolved CO2 to the bottom of the ocean. In upwelling currents, the opposite occurs as coastal water warms brings CO2 back to the surface. Increased temperature decreases gas solubility, and decreased temperature increases gas solubility. So colder waters will be able to absorb more carbon dioxide and take it down to the depths, and warmer waters won't be able to absorb it, and so it will rise up back to the atmosphere. The biological pump has to do with aquatic organisms like algae who move carbon through their biological functions, converting carbon into different forms. Russ George was targeting a key organism in the biological pump, phytoplankton. Now, phytoplankton are one-celled organisms, microscopic marine algae that use photosynthesis just like plants on land. Photosynthesis occurs via this reaction. Carbon dioxide, water, and energy from light react together to form glucose, oxygen, and water. The energy from the light is bound in the sugar, the glucose, and this provides nourishment for plants and algae. One key nutrient that's part of the chloroplast is the mineral iron. In plants and algae, iron is a key part of proteins that transport electrons and aid in the synthesis of chlorophyll. Without iron, plants and algae can't make chloroplasts. They can't photosynthesize. Plants are absorbing iron as Fe2 plus ions. There are a lot of complicated transport processes that occur in chloroplasts in plants and in mitochondria in humans, for instance. Not all clearly understood, as you can see by question marks. What is known, though, is that iron is extremely important, and the atomic ratios of critical nutrients in plankton biomass are expressed by the Redfield ratio, which says you have 106 carbon to every 16 nitrogen to every phosphorus atom. And that was also expanded to include iron, which said that you had 3,000 carbon atoms to 58,000 nitrogen to 3,600 phosphorus for each iron atom. So as long as they get the nutrients they need, plankton can perform photosynthesis, and this will consume carbon and produce oxygen. And when these plankton die, some of them will settle to the sea floor, capturing and sequestering the carbon. According to the expanded Redfield ratio, if they have iron, they will be sequestering a lot of carbon for every bit of iron they have. Now, like phytoplankton, diatoms are another form of algae. Single-celled diatoms in the ocean also need iron to survive. But diatoms can create stores of dissolved iron to use when concentrations in the water become low. Diatoms can pack iron away in a storage organ vacuole or by synthesizing the protein ferritin, which it can then break down into iron when needed. Shelled creatures as well, as I mentioned before, they're made of calcium carbonate, so when they die and get lost in the sea floor, just like the algae, they can sequester that carbon. So that's the biological pump. In the ocean, there are two types of iron oxidation states that are extremely common, Fe2 plus and Fe3 plus. Now, Fe3 plus compounds are insoluble, and in areas where phytoplankton are scarce, but would otherwise grow according to the conditions, there are low concentrations of dissolved iron, or Fe2 plus. The hypothesis is that flooding the sea with soluble iron, or Fe2 plus, would lead to a stimulation of plankton and algae growth, and then this would cause sequestering of carbon dioxide from the excess algae. This is known as the Martin hypothesis. Oceanographer John Martin theorized that the biological pump could be manipulated by adding iron 2 sulfate to sunny ocean waters, causing algae blooms where there weren't algae blooms previously. These algae blooms would be eaten by local populations, but also sink to the seafloor and sequester carbon. Martin famously said that he could create another ice age with just half a tanker full of iron. It's a bit of hyperbole, but it was John Martin who inspired geoengineers like Russ George to fertilize the ocean with iron. Now, why is iron so special? Well, it's simple. Iron plays well with others. Due to its electron configuration, it can have different oxidation states, not just 2+ and 3+, although those are most common. Iron 2 has 4 unpaired electrons in its 3D subshell, making it an attractive option for reacting and bonding with other substances. In coordination chemistry, it's common to can have iron as a metal ion complex with ligands forming complex molecules. This is commonly found in essential proteins in organisms. Iron helps tie everything together. Plants use iron to synthesize their chlorophyll and in their proteins. Humans use iron-based proteins like heme to transfer oxygen in the body. The question is, are they right? Will iron fertilization help stave off global warming? Well, no. After Russ George fertilized that ocean water, algae did bloom, a lot of algae. And did it happen because of the iron seeding? Well, most likely, because we have seen this in other experiments with iron fertilization. There have been at least 13 iron fertilization experiments, and they all result in algae blooms. However, this doesn't prove the second part of John Martin's hypothesis, that carbon will be sequestered by these algae blooms. So while Russ George did create an increase in algae, and even an increase in salmon runs in the 2 years following his experiment, he was not able to show that significant amounts of carbon dioxide were sequestered in the seafloor. A similar iron dust experiment in the year 2000 showed the same algae bloom, but again did not show carbon sequestering on the seafloor. Satellite evidence, in fact, showed that the iron mostly stayed in surface waters rather than going down to the depths, where it would cause long-term change. Carbon is not sequestered unless it settles down to the ocean floor, where it can remain for millions of years. Most of the carbon that sinks from plankton blooms is dissolved and remineralized well above the seafloor, and going from days to years, it will eventually return to the atmosphere, and this defeats the purpose. It was estimated that in the Eyes and X experiment, only 10 to 20% of the resulting algal bloom died and sank all the way to the sea floor. Now, John Martin based his hypothesis not only on measured deficiencies of iron in certain sunny areas of the ocean, but also on glacial record. Ice core samples showed a correlation between iron dust in the atmosphere and periods of global cooling and carbon dioxide reduction. Knowing that phytoplankton used that iron, Martin hypothesized it was the iron dust that was responsible for the cooling during those periods in the past. But it's not actually clear that the iron dust led to the global cooling, or if it was a coincidental occurrence, or if something else triggered both the cooling and iron dust to occur and an increase in the past. According to recent computer modeling, the only area where there would be a significant impact to reducing carbon dioxide would be the Southern Ocean. But that would only work if the carbon dioxide is taken all the way to the bottom. And as I said before, this doesn't seem to happen in these iron fertilization experiments. The results are just not there. Now, besides the fact that it doesn't work, it's also actually harmful. These experiments focused on the positive aspects of algae bloom, that is, the sequestering of carbon dioxide and the expelling of oxygen, and the increase in animal populations as they eat that algae. However, a significant side effect is what we call toxic algae bloom. Toxic algae bloom can just refer to excessive growth of any algae or to specific types of algae that produce harmful toxins to other organisms. Overall, excessive growth of algae is not actually a good thing. Algae growth so that animal populations can grow is a good thing, but in general, you shouldn't be manipulating the biological pump this way, because there are consequences. Overabundant algae consume the nutrients in the water and eventually die. And when they die, regardless of whether or not they sequester carbon, the majority will be broken down by bacterial processes. Bacteria use up oxygen recycling the overgrowth of algae, and they use up so much oxygen, in fact, that sometimes they can create what are called dead zones, anoxic areas where aquatic life like fish cannot survive due to the lack of oxygen. This means that the algae blooms that were initially meant to produce oxygen through photosynthesis will destroy ecosystems by consuming that oxygen. One word for this is eutrophication, when you have excessive growth cycling into death. Oxygen in water is referred to as dissolved oxygen. Dissolved oxygen, or DO, can come directly from the atmosphere or from photosynthesis. DO levels reflect the amount of oxygen available to living organisms such as fish and mammals. Dissolved oxygen levels are directly related to the ocean's ability to support aquatic life. Oxygen gas from the atmosphere is only somewhat water-soluble because it's a nonpolar gas and water is a polar molecule, and like dissolves like. A dissolved oxygen level of 6 milligrams of oxygen per liter is required to support marine life like fish and water. Oxygen saturation, however, is related to temperature. At standard temperature, 25 degrees Celsius, approximately 8 milligrams of oxygen can dissolve in 1 liter of fresh water. The higher the temperature, the less oxygen will dissolve in the water. Seawater is quite salty, and this salinity also decreases the amount of dissolved oxygen. At standard temperature, approximately 6 milligrams of oxygen can dissolve in 1 liter of open ocean water. Now, since the ocean is naturally less saturated in terms of dissolved oxygen, it can become even less so because of eutrophication. During eutrophication, the decomposition of the excess organic matter from algae and anything else that has died is done by decomposers, bacteria, fungi, and microorganisms, who feed on the organic matter and transform it into inorganic matter. Nutrients from the decaying matter, such as phosphorus, nitrogen, and sulfur, are recycled into oxygenated compounds, phosphate, nitrate, sulfate. And the common thing to these compounds is oxygen. The bacteria are using oxygen to break them down in the process of aerobic decomposition. In the meanwhile, when they break it down, they release the carbon back as carbon dioxide. Carbon dioxide becomes carbonic acid in the water, and you go right back to making the ocean more acidic. And of course, there are anaerobic bacteria that actually turn carbon into methane gas, or CH4, which is another greenhouse gas that is even more toxic. And of course, the more food that's available, the dead matter, the more the bacteria will reproduce and respirate, taking up more of that dissolved oxygen. And without that dissolved oxygen, you can't have life. Now, as the life that will survive during the algae blooms, you have to realize that any species that can get the iron first will be more likely to survive. So remember how efficient diatoms were at storing away iron? Research into algae blooms has shown that diatoms can reduce the amount of iron available to other plankton because of this efficiency. And this means that iron fertilization would affect biodiversity, making more diatoms and less phytoplankton overall. This becomes a problem because the pseudonychia diatom species in particular can produce toxic domoic acid, and this is a very harmful poison that can infect an entire food chain. Domoic acid poisoning in humans causes seizures, amnesia, and paralysis. Now, these buggers, the pseudonychia diatoms, are less abundant in open oceans, but they are extremely responsive to iron. The reason why they have been found in open oceans is because of natural weather events like dust storms and volcanic eruptions. So you have these small pockets of pseudonychia, but normally pseudonychia will be found in the coastal regions where you find cases of shellfish poisoning. If you dump a large supply of iron into the ocean, what you will find is the pseudonychia can proliferate, and this will lead to even more food chain poisonings in the open ocean rather than just the coast. Another problem with algae blooms is that they can take up the surface of the water. They can cause darkness by limiting the amount of light that penetrates the water itself, and plants and animals underwater that depend on this light will die off. Even predators that require light to hunt won't be able to get their food. So those are just some of the harmful effects of these algae blooms, these artificially created, manipulated events in nature that iron fertilization or seeding experiments cause. But even if these harmful effects weren't so serious, you have to realize that we are still putting too much carbon dioxide in the atmosphere than any iron seeding experiment could fix. Globally, the oceans have 67 billion tons, that's TONNES, of carbon dioxide. And 1 TONNE is about 1.1 tons. Even John Martin's best estimates in his lab predicted that every ton, TON, of iron would only remove 110,000 tons of carbon from the air. So mathematically, we can estimate that you would need about 670,000 tons, TONS, to sequester all the carbon that has been absorbed in the ocean from excess carbon dioxide. That is a lot of iron. Whereas George only dumped 120 tons and he caused a local algae bloom. So can you imagine if we took all our iron stores and threw it into the ocean, how much algae would bloom, how much the ecosystem would be affected, how many dead zones you would have, how many outbreaks of toxic algae you would have? In essence, it would just be another form of pollution. We are already polluting the atmosphere. We should stop polluting the atmosphere. We should definitely not pollute the ocean just because we're polluting the atmosphere. Humans should be lessening carbon emissions, not dumping iron into the oceans to counteract those emissions. It was extremely irresponsible of Russ George to dump all that iron without thinking about those consequences, to focus on carbon credits and salmon rather than the entire picture. There have been at least 13 large-scale iron fertilization experiments, and they've all produced inconclusive results when it comes to carbon dioxide reduction. Geoengineering is targeting the wrong problem, and it doesn't work.